Friends, welcome to the 30th lecture. We are going to discuss now in this set of lectures details about curved beams. Curved beams can be classified into two sections. One, beams with small initial curvature, two beams with large initial curvature. Though there is no clear distinct difference in the definition of 1 and 2 sections, however, literature says when the ratio of initial radius of curvature to the depth of the section if this ratio exceeds number 10, then it belongs to classification of beams with small initial curvature. If it is the other way, then it can be classified as beams with a large initial curvature. Our interest is now to study bending of curved beams with small initial curvature. Let us take a beam. Let us say, let us define certain geometric parameters of this beam. Let us choose a layer whose radius is r measured from here. This point is O. Now, let us select a fiber which initially has an angle d phi. Let us say this fiber intersects, or this cross section intersects at A, B at the extrados and C and D at the intrados. Let us say this is my intrados, this is my extrados. When I now apply a moment m, the curvature will now change. Therefore, the points P and Q will now shift and tilt to shift the new center which I call as O dash, and the new angle is d phi dash, and the new radius is r dash, and the fiber distance is y. So, I have a typical cross section which has got n axis, and I have selected a point, and that point distance y, which corresponds to any point on this, let us say the point this one. Okay. Now, let R be the initial radius of curvature, d phi be the angle subtended at the center of curvature by the element A, B, C, D. R dash be the radius of curvature after moment m is applied. Interestingly, one can note that r dash will be lesser than r, because the applied moment will tend to close the curvature. I can give an example. Take a straight bar, I would say the curvature is infinity. When you bend the bar, it has some curvature whose value will be r dash, and r dash will be lower than r, because any moment which closes the curvature will always reduce the radius of curvature, and d phi dash is the angle subtended by the element after deformation. Having said this, let us now consider a fiber PQ at a distance y from the neutral axis. Y neutral axis, can see here at this point there is no change. Therefore, the black line what you see here is the neutral axis, which is n n, which you can see in this section also n n. So, now original length of the fiber is actually r plus y into d phi. Now, length of the fiber after application of moment is r dash plus y into d phi dash. Therefore, one can easily find change in length of the fiber, which will be r dash plus y d phi dash minus r plus y d phi. So, the strain of this fiber will be change in length by the original length, which I call equation 1. Interestingly, as the length of the fiber at the neutral axis remains unchanged because it does not deform, I call that length as ds, which will be equal to both r d phi as well as r dash d phi dash, which implies that r d phi is r dash d phi dash is ds. Let us substitute equation 2 in 1. We get strain now as y of d phi dash minus d phi by r plus y d phi. This is equation 3. In the above equation, y may be neglected because y will be very small compared to r. Hence, strain is now y d phi dash minus d phi by simply r d phi. I call this equation number 4. Now, from equation 2 we can simplify equation 4. Epsilon now can be y, I should say d phi dash by r d phi minus y d phi by r d phi which I can say as y d phi dash by ds minus d phi by ds, which can be simply y 1 by r dash minus 1 by r. I call equation number 5. But we know strain is actually stress by Young's modulus. Therefore, y 1 by r dash minus 1 by r is strain by this. It means sigma by y will be E times of 1 by r dash minus 1 by equation number 6, which is a classical equation of bending for curved beams. There are some assumptions in this equation. Which are actually similar to straight beams. Let us see what are these assumptions. 1. Every cross section of the curved beam remains plane and perpendicular to the centroidal axis before and after application of external moment. The second assumption is very interesting. Now, to satisfy the above condition, we need to impose one condition that one should agree that net force acting on any cross section of the curved beam should be 0. Then only the above condition can be meaningful. If this condition is violated, if it is not so, then it may result in warping. So, mathematically dA, the force, should be set to 0. So, now let us substitute equation 6 in equation 7. We get integral E y 1 by r dash by r of dA should be 0, which I say E 1 by r dash minus 1 by r integral A y dA should be 0. Since E by r cannot be 0, integral y dA should be set to 0, which means that implies that the geometric axis of the curved beam should coincide with neutral axis of the curved beam. So, that is a very interesting statement we derive from this understanding. Further, as the curved beam is in equilibrium condition under the applied moment m, one can agree to state that sigma y dA should be actually equal to this moment. Now, substituting for sigma in the above equation, because we already have an equation for sigma, you can see here we already have an equation for sigma. Substituting this in the above equation, E 1 by r dash by r y square dA should be m, but we know that integral y square dA, the second moment of area, is actually moment of inertia, and hence E 1 by r dash by r into I is m, that is m by I is E times of 1 by r dash minus 1 by r. If you combine this equation with equation 6, which is this equation, which is sigma by y is equal to this. So, now we can say m by I is also sigma by y, which is E by r. Instead of that, it is r dash minus r. So, that is my classical equation for bending of curved beams. So, friends, interestingly, based upon the assumption that the geometric axis of a curved beam will align with the neutral axis of the curved beam, while the moment applied decreases the radius of curvature, one can easily say that this equation is valid for curved beams with small initial curvature. Let us now proceed to find deflection of curved beams with small initial curvature. We use Castigliano's theorem to derive the deflection. So, to use this theorem, we must have an equation for strain energy. So, let us try to find the expression for strain energy. U is generally given by half m delta d phi for curved beams. Equation 1, where d phi is the change in angle produced by the moment. M at the center of curvature. I think it should be d phi dash. We also know that m by I is E of 1 by r dash minus 1 by r. Let us multiply ds on both sides. So, m by I ds is E ds by r dash ds by r. Look at equation 2. We already know that length of the fiber at neutral axis remain unchanged, and we said ds is as same as r d phi, which is same as r d phi dash. Hence, m by I ds can be now said as E times of d phi minus d phi dash, that is m ds by E I is delta d phi, equation 3. Now, substitute this in equation 1, we now get strain energy is integral half m square ds by C I by partially differentiating u with respect to p, we get delta, which will be dou u by dou p, which will be m by E I dou m by dou p of ds, equation 5, that is the deflection. Similarly, to get the angular rotation, may be obtained by partially differentiating u with respect to angular moment m 0. So, I get theta, which is this by m 0, which is integral m by E I dou m by dou m naught of ds. So, friends, in this lecture we understood the basic geometry of curved beams with large and small initial curvature. We derived the equation of flexure for curved beams with small initial curvature. We also derived equation for deflection and angular rotation of the curved beams with small initial curvature. We will extend this discussion for beams with large initial curvature, then extend this to find out the stresses at the intradas and extradas of the curved beams, which is a very important assessment in terms of curved beams used very commonly in offshore structural platforms. Thank you.